is Jasmine. I'm here doing a presentation on the ideal gas formula. Let's start off with some characteristics of gases. Physical properties of gases are all similar, composed mainly of non-metallic elements with simple formulas and low molar masses. They expand to fill their containers, are highly compressible, and have extremely low densities. Two or more gases can form a homogeneous mixture, which is very important to know about gases. Well, let's talk about some properties that we will define later on through three different laws: Charles' law, Boyle's law, and Avogadro's law. Properties that define the state of a gas sample: temperature, which is measured in Kelvin when it comes to the ideal gas formula; pressure, which is measured in atm, torr, or possibly sometimes it can be measured in, I believe, dealing with mercury, millimeters per H, which millimeters per mercury. Volume, which is always measured in either milliliters or liters, and the amount of gas, which is the number of moles, which is measured in moles, unless you're trying to find the molar mass or determine something along those lines. And we'll go over that in the example that I have for us today. So, our first law that we will learn about today is the Charles' law. Charles' law basically states that V equals T. And what it means by that is saying that volume of a fixed amount of gas at constant pressure, it has to be constant pressure, now remember that, is directly proportional to its absolute temperature. When two measurements are directly proportional, as one changes in size, the other will do the same thing. So it undergoes the same change, same size change, same distance, doesn't matter. So if the volume goes up, the temperature will go up. If the volume goes down, the temperature goes down. It's a directly proportional relationship. The equation goes V equals constant times T. So in order to get T on the other side, you divide by T, and it's V over T equals the constant, in which you could do V over T equals V over T, V1 over T1 equals V2 over T2, which means you can find the volume of a different container, or if it's like a tube and it's a latch on top of it, you know, you want to find the volume of the other half, you can do that with this formula. Next law we'll talk about, let's check this out because getting stuff done. Next law we'll talk about is the Boyle's law, which basically states that volume is inversely proportional to pressure, meaning that it's V over 1. V equals 1 over P. Basically stating that the volume of a fixed quantity of gas at constant temperature is inversely proportional to pressure. So unlike Charles' law and Avogadro's law, which we will talk about after Boyle's law, P and V are inversely proportional, meaning that when pressure goes up, volume goes down. When volume goes up, pressure goes down. So it's not a direct relationship, it's an inverse relationship, meaning that not that they don't like each other, they just go opposite whenever they're being dealt with. So if one is very high, then you know the other one is very low. So if you ever do an equation and you're solving for one of them, and let's say your volume is super, super high, and you get a result that your pressure is high too, then you know that something's wrong. Especially if the pressure value is a lot larger than the volume itself. And the equation for that is PV equals constant, which is P1 times V1 equals P2 times V2. And you can use this equation anytime you're trying to find the volume or the pressure of another system, or even in a system within itself. Another law we'll talk about today, which I'm super excited about, is actually one of my favorites. If I can find it. Should have this together. All right. Here you go. Alright, sorry. Let's check that out. Alright, this is the last law we'll learn today, and it's all these laws relate back to the ideal gas equation. So, just keep that in mind when you're doing your formulas, that all of these can go just along with this one. Alright, so Avogadro's law basically states that the volume of a gas at constant temperature, remember these constants are super important, so constant temperature and pressure is directly proportional to the number of moles of the gas. Okay, so when dealing with something called the standard temperature and pressure, we will talk a lot about this when we come to gas densities and things of that nature. T equals 0 degrees Celsius, or T equals 32 degrees Fahrenheit, it will equal 273.6 0.15 Kelvin. And the pressure is 1 atm, and the volume is 22.4 liters for 1 mole of gas occupied. That is also very key as well. So basically, Avogadro's law basically says that V equals constant times N, which when we talked about Charles' law, how V, equals constant times T, is the same concept. You're dividing by N on both sides, and you get V1 over N1 equals V2 over N2, which is really easy to remember. Stuff, all of it goes together. It doesn't. None of this is hard. It's not hard to remember. If anything, the hardest part you'll have remembering is the R constant, which I have a little song for that, and I'll teach you that at the end. All right. Now we get to the moment we've all been waiting for. The ideal gas law. So, well, it's not a law, it's a formula. So basically, combining all of the 3 previously learned laws that we just talked about, Charles' law, Boyle's law, and Avogadro's law, we can say that it gives off this proportional idea that V is related to NT over P. So volume plays a huge role in, the existence of those 3 moving parts. And in order for this to work, it needs to be to equally, like an equilibrium formula equal to work together. That's not correct, but basically what I got from it was that it has to be equally related. They use a constant proportionality, which is R, and it is recognized as 0.08206 liters times atm divided by moles times Kelvin. And the formula is just itself. PV equals nRT, which is not hard to remember. If anybody doesn't remember PV equals nRT, we'll get you some help, but that's pretty easy. So let's do a problem. Why don't we? All right, let's move on. Stop it. Alright, so the problem reads, a balloon has a mass of 0.5 grams when completely deflated. When it is filled with an unknown gas, the mass increases to 1.7 grams. You notice on the castaner of the unknown gas that occupies a volume of 0.4478 liters at a temperature of 50 degrees Celsius. You note that the temperature in the room is 25 degrees Celsius. Identify the gas. So they want us to identify the gases within the balloon, which is not very hard to recognize. All you have to do is really use your equation that we talked about earlier, which is PV equals nRT, not hard, see the gas. And also, we're going to start off with recognizing a few things that are going on right now. So the first thing is, hopefully you noticed that they gave us 2 different temperatures. They gave us 50 degrees Celsius and they gave us 25 degrees Celsius. It's key to recognize those things even if you don't understand what the question is asking for firsthand. Recognize when they're giving you multiple things, because automatically that's going to give you one of these equations. One of these equations are going to be used. Because when they're giving you 2 different things, especially if they're giving you a value and a temperature, you automatically need to take Charles' law, and you automatically need to take V1 over T1 equals V2 over T2. Automatically, no questions asked. That's just the thing that you must think about. So for me, before I go into detail about that, let's go ahead and do some conversions. It's important for me at least, I think you should convert early so then you don't have to worry about it later. So remember we talked about how, liters, let's say this was in milliliters. So if it was in milliliters, it would have been, but this would have been moved over 3 times, and then 447.8 milliliters. If you wanted liters, you would have to divide by 1,000. But for degrees, we always, remember I told you that we always want our ideal gas to be in Kelvin. We have to have it in Kelvin. So with that being said, we have to convert Celsius to Kelvin. And that's easy. The simple formula to remember is just K equals volume degrees Celsius plus 273 Kelvin. Really easy to remember. You may not be able to see it, but it's literally this amount plus 273 Kelvin. It's not that hard to remember. So with that being said, we do 50 plus 273. Pull out our little thinking caps here. And we get 323 Kelvin for this one right here. So we're going to put 323 Kelvin. And then right here we have 25. So we're going to do that one more time. We're going to do 273 plus 25. 8, 9.
And it's just
So we have 298 for 25. Alright, cool beans, great. So we've converted our Celsius to Kelvin both ways. And we've also made sure that we had liters here. So let's read over the question again. Let's read over it one more time. It says that you notice on the Casimir, and the Casimir is just like a replacement where the balloon goes. It's really simple, it's not hard. It's not really important. That's another story. Of the unknown gas, which is what we want to know, that occupies a value of 0.4478 liters at a temperature of, now that we have it in Kelvin, we're going to put it in Kelvin, 323 Kelvin, I'm sorry. You know the temperature in the room is 25 degrees Celsius. Identify the gas. So with that, since we have the liters, the value of the temperature as it is occupied on the Casimir, and we have the degrees as it's occupied on the Casimir, we can do V1 equals, remember when we talked about V1 equals T1 and all this other, we can use that formula now. That's cool, right? That makes sense. Yay, also, we can use the formula. So I'm going to put it down here.
what the what?
Alright, so here it goes. We have our V1 over T1 over V2 over T2. It's like, why is she on the ground? She's trying to make sure you learn. Alright, so you take your value, which is 0.4478 liters, divided by your temperature, which is 323 Kelvin. Alright, and you set it equal to your V2. We're going to erase this stuff over here because it's going to get confusing, and I don't want you guys to get confused. I want you to learn something. V2 over, which we already have, are 298 Kelvin, right? So this is just simple math. If you remember anything about algebra, basic geometry, things of that nature, you don't. I know everybody remembers cross multiplication. Very simple. All you have to do, cross multiply and divide. Cross, divide. Really easy. And so with that, you get a value that is equal to X. Let me get my calculator. I'm a math whiz, but not that great. So you do 0, you do your liters times your Kelvin, and then you also divide by Kelvin. And you see with that, remember when we talked about we get rid of the things that we don't want. So we don't want Kelvin anymore. We don't want it. We're done with it. It's going to be whatever this value is that I gave you. This is going to be liters per Kelvin. And with that, you can cross it out because it's one on the bottom, one on the top. That's it. Alright, and our value comes to, let me get a different color so you guys can see it. Our V2 value, which is not our answer, remember, we're looking for the ID, identifying the gas in the system. Alright, so our value comes to 4.413 liters, okay? 0.413 liters, which is very important because we're going to use this, we're going to put it back into another equation that you will find very familiar. Yes, listen, this is time consuming. I know you're probably like, oh my gosh, why are we doing so much? Because it's, honestly, when you have extended problems like this, you're able to learn more about the different equations and how they apply to PV equals nRT. And then you're like, okay, this is an advance, I'm ready for the test. It's really easy.